So the last lecture ended talking about the maximum likelihood estimator from finding it from a function, and how it can be the same estimator even if the height of the function is different because the sample size is different. So it turns out the maximum likelihood estimators are super important, and they are the key things for the shortcuts I talked about, where you don't have to compute the likelihood of every possible model every single time. So we have data that we've collected and a model we think best represents the real-world process that created the data, and the maximum likelihood estimators are the parameters for our model that have the best possible support from our data. We can't do any better. There won't be any set of parameters that have any better likelihood. And there are some cases where the maximum likelihood estimators can be hard to find. So we didn't get P8 to be exactly 1/3. We saw that it was near 1/3, and we could tweak the ranges, and we could guess, and that can be, if you have a very complicated model, the way people find maximum likelihood is they get closer and closer to where they think it is and tweak the parameters around to get them. You can see that once you get more than one or two parameters, that can be really hard because you have to tweak each parameter separately, and it can take a really long time. Fortunately, there are maximum likelihood estimators that have been proven with mathematics to be the MLEs regardless of without any twiddling. So if you have a discrete random process, the maximum likelihood estimator is the proportion of times each outcome occurred. So that's the number of times that outcome occurred divided by n, like we saw with the Bernoulli example. And that generalizes across other non-Bernoulli examples too. If we have a normally distributed random process, then there are two parameters we have to estimate, the mean and the standard deviation. And it turns out that the sample mean and the sample standard deviation are the maximum likelihood estimators for that. So if I give you some data and I ask you what the maximum likelihood parameters are for a normal distribution, you don't have to compute a likelihood function. You can just calculate the mean and standard deviation of the sample. Likewise, if I give you some discrete data, you wouldn't have to compute all the different likelihoods. You could just find the proportions, a proportion of outcomes that belong to each category, and then you have found the maximum likelihood estimators. So that saves us a lot of time. And that's the test that we're going to look at next week. All of those have demonstrated maximum likelihood estimators, so we don't have to go through the whole long process of finding the formula, computing the likelihood of each observation, the probability of each observation, and multiplying them all together to get the likelihood of that particular parameterization of the model. And that is it for this set of lectures.